So if the angle it makes with the floor is 50 degrees, calculate the reaction forces at both ends. What is the coefficient of friction? Coefficient, I hope you guys know this by now, coefficient is mu, right? Because friction, when the equation is friction equals to mu r. Mu is the coefficient, r is the reaction force. All right. So here we have a rigid body that is in equilibrium, which means that it's not moving in the x and y direction, it's also not rotating. So that is what it means when we have equilibrium system. So the net torque is equal to 0 and your F net is also equal to 0. This is the two conditions. Okay, so a little recap there. Okay, sorry for the disturbance. Lepas tu, we have to draw the free body diagram, right? And let me use a different color. This is also blue. So let's use pink. So the center of mass, okay? If you guys still remember from last week, the center of mass is mg. Your mg is at the center lah, center of mass. So mg is the weight of the beam. Okay, this is due to gravitational force. That's your first force. And then I told you for torque, you need to determine the axis of rotation. And using our prop last time, I told you, oh, tak nampak. Using our props last time, why is my to-do like that? Okay, so this is the wall and this is the floor. And I told you that the floor is rough, right? So axis of rotation should not ever move. If you want to decide that it's an axis of rotation, your axis of rotation should not be moving. So let's say this guy is moving like this, right? So it means that it's not the axis of rotation if it can move like that, because axis of rotation needs to be stationary so that the rest of the body can move in rotating position, right? So if my axis of rotation is at the center over here, right? So the rest of the body can rotate, but the center remains at my finger. So remember, the axis of rotation should not move. Okay, so that's a trick to determine the axis of rotation. Okay, so here it says that the floor is rough, which means that it's supposed to be not moving, right? So if it's not moving and this guy is smooth, the wall is smooth, which means that our axis of rotation should be at the bottom of the ladder. If you want to say the axis of rotation is on the wall, it means that the rest of the body should be rotating except for this part, right? So if we can imagine this is our ladder. This is my axis of rotation, the wall. So your ladder is rotating like that, which doesn't make sense, right? Like, how does it defy gravity? I don't know. So it's just not possible. So if our axis of rotation is down here, is it logical? So I can jatuh macam ni, my ladder can fall like this. Okay, it makes sense. And the friction prevents it from moving, from some sliding off. If it slides off, it will go like this, right? That is if the floor does not have friction, but it has friction, so it will fall like this. Okay, so we already talked about friction now. So if it's going to fall, it will fall this way, right? The motion to fall is this way, which means that our friction should be this way, should be opposing the falling motion, but it's not falling because we have friction. But let's say we don't have that friction, the motion to fall will go to the left. So that means to prevent the ladder from falling, the friction should be to the right, opposing it. Okay, is that clear? Okay, yes. Friction and mg. So far we are talking about friction and mg je baru eh. And then I also told you last time that your axis of rotation should have reaction force for torque specifically. Okay, so untuk torque, we have to remember that we are only considering perpendicular forces. So if I wanted to make this, if I want to like label this, I want a reference to see where is my perpendicular force should be. Where should my perpendicular force be? So I'm going to draw the dotted lines. Okay, so if my force is perpendicular to the beam, it should be in this direction, right? And I told you, because you don't know which way is your reaction, you should put it at an angle. So last time we saw this beam, if you guys still remember, we saw this beam and it was fixed to a wall, I think. Yeah, a wall was it? But this was the axis of rotation, I remember. And the contact point is here. So if I were to use, if I were to write reaction the way I did it before in chapter 3, I would write, okay, so this is the contact point. So a reaction force should be this way. But it doesn't make sense, right? Because you are going into the beam. So what we did was, we put, okay, let's just put R so that it has X and Y components so that we can solve for it and it's not going into the beam completely. So that is when your wall is, the contact point is like that. Right now, if I were to say, if I wanted an angle, I could still write it like this. If I wanted an angle for my R, we should use pink. Yeah, I could still write it like this. Okay, from chapter 3, we know that whatever touches reaction force is the force when we have contact. So now the ladder has contact with the floor. My reaction force should be going upwards. But this clashes with what I told you about the axis of rotation. Okay, hear me out first. So I told you reaction force should have X and Y, blah, 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 right? But this is the perpendicular direction. And I said I wanted an angle. This is the perpendicular direction to the beam. If I write my R like this, I still have that angle. So it does not clash with the torque thingy. Does that make sense? So I can still use my reaction force that I learned from chapter 3, which is, it is perpendicular to the surface. So that's my reaction force. Okay. Again, I'm going to repeat myself. From chapter 3, we learned that reaction force should be perpendicular to the surface of contact. So here, our surface of contact here, I'm talking about this guy. Ya Allah, apa benda ni? I'm talking about this particular instance. The reaction force should be perpendicular to the surface. Okay, so it is perpendicular. Why? 90 degrees. Does it have an angle to the axis of rotation? Yes. This is the apa nama dia? Perpendicular direction. My R is like this. This is the perpendicular direction. My R is like this. Yes, it has an angle. Okay, back to chapter 3 punya reaction force tadi. We have another point of contact, which is this R over here. And I told you from chapter 3, the reaction force is perpendicular to the surface. So the surface is the wall. This is our R. Now, is this R, the R on the top, R1, equal to the R at the bottom? Can anyone tell me? Is it equal or is it not? No one? No one knows? No one wants to try? Okay, so the answer is no, it's not equal. This point over here has friction. This point over here doesn't have friction. Kat situ pun dah lain dah. But in general, it shouldn't be the same lah. Because it's two different places. Okay, so this ladder is not moving. So it has these two conditions. Net torque is equal to 0. Net force equals to 0. So let's write it down. Okay, so I'm going to erase this. Oops. Any questions? Okay, so far? Okay. Yep, question? Ada? Okay. I'm drinking coffee, by the way. Okay, so that is, we start with force because I like force better than torque. So my net in the Fx is equal to 0. That's my condition. Writing your condition and then write the equation write the forces in your free body diagram into the equation. So in the x direction, I want to say this is my x, this is my y, the typical one, the conventional one. So in the x direction, I have friction to the right. I'm going to say that's a positive. So I have reaction force to the left. That's a negative because it's in the opposite direction. Okay, so everyone is following me so far? Okay, tak panic kan? So R1 is equal to friction. That's our first equation. Second one, F net in the F net in the Y equals to 0. That's my condition. Write the forces in my free body diagram. What is acting in the Y direction here? So I have R2 going up over here. R2 going up. What is going down here? I have mg. So minus mg equals to 0. So R2 is equal to mg R1 friction. Okay, betul. Mg. Okay. That is my example. Sorry. Okay. So we know that mg, m is 20, right? And g is 9.81. So this gives me R2 of 196.2 newtons. Okay. I solved for R2, I did not solve for R1 yet. Because why? I don't know what my friction is. What's the equation for friction? The equation for friction is mu R. Which R should be in this equation?
R2.
R2. Why?
Sebab itu yang ada friction.
Kat situ yang ada friction. Betul. Betul. That is where the friction is. So your R should be where the friction is lah. So the friction is at R2. So this equation becomes mu R2. Okay, so we know that, yeah. Excuse me, slow it down. Yeah. Kalau tak duduk luar, okay? Okay, so R1 equals to mu R2. Yeah, tuang ni. Okay, so that is your equation. And we already solved for R2. But we don't know what R1 is, so stay tuned. Lepas tu, we use the second condition, which is net torque equals to 0. Don't have enough space. So let's drag this over here. And then we can delete this. Okay, so let's do the torque one. I'm gonna use blue now. Okay, so net torque is equal to 0. And the equation for torque is RF, so don't get confused. So here I need to resolve my forces in the perpendicular direction to the beam. So this becomes theta, and this becomes mg cosine theta. Sekejap bising lah. Okay. Where was I? Okay. So RF, So we need the force to be perpendicular. So that is that. Alamak, apa macam tu? Okay. So the perpendicular force to this is mg cosine theta. I need to know what is the angle over here. Okay, so yeah, sebelum tu, how did I know this angle was theta and not 90 minus theta? So if you guys remember, we have an incline from chapter 3, chapter 4, chapter 5. We have an incline, and when there was an mg in our free body diagram, so mg, we resolved it. So the theta was here, right? Mg cosine theta. So sama juga, this is almost like an incline, even though it's a ladder. It looks like an incline, so this is 50, this is also 50. So I'm just explaining to you guys in case you're wondering, how did I decide that that was theta? Okay, so next, moving on. Where is the other, where is the other theta? Okay. If you guys can see here, we have a Z punya, we have a Z shape here. So this guy is 50. This guy should also be 50. So that's another angle. What should be the angle over here? So I'm going to erase the 90 degrees here. So here is 90 degrees. So this makes it 40, right? This is a 90. So tolak 50, you get 40. And then this is also 90 to the beam. So if this is 40, this should be 50. So the angle between R2 and the perpendicular direction is 50 degrees as well. Okay, so those are your angles. So that is a 50. Let me erase that. This is 50. This is also 50. Okay, so that's angle je baru, because we need to resolve our forces to be perpendicular. And I told you, whatever force that goes through the axis of rotation does not contribute to torque. So we can just not write it. You can write it down, but you can put a 0 there. So sama je. So I'm not going to write it. So we are only going to focus on the mg and the r1 because yang tu je yang tak lalu dekat axis of rotation. So mg is going this way. So it's going clockwise. So it becomes a negative. So mg cosine 50. And the length is L over 2 because it is at the center of the beam. And the length from the axis of rotation is L over 2. I don't know what my L is. Do I know? Yeah, I do know what my L is. Okay, pas tu, my R1, resolving it to be perpendicular, my R1 would be this way, right? So this is R1 sine 50 because it's not touching the angle, so it gets a sine. So that is going in the anti-clockwise direction. Okay, I told you how to figure that out. Use a ruler or whatever props that you have if you can't imagine it. So R sine 150 and the length is L. Okay, because it's the length from the axis of rotation is the entire beam, so it's L. Okay. Macam mana nak buat ni? Kita cuba tempat. Let me move this here. Okay. So now let's solve that. So my mg, I know what my mg is. It's 20. Oops. It's 20. 9.81 cosine 50 L over 2. I'm shifting the mg to the other side, which gives me R1. Do I know what my R1 is? I don't know what it is. Divided by this guy, I'm going to just shift whatever that's left. Sine 50 over L. So now I can potong this one and then just solve it. I know what cosine 50 is. I know what sine 50 is using my calculator. So R1 is, what is it? 82.3. My R1 is 82.3 newtons. So now I have my R1. I know what my R2 is. So I can just substitute into this equation, the first equation. So R1, so mu is equal to R1 over R2, and R1 is 82.3 divided by 196.2. The answer is the answer is 0.42. Okay, so mu is 0.42, no units. That is your final answer. Okay, so that's the end of this problem. Any questions or any confusion about this one?
Doctor,
Yep,
the vertical wall is it's smooth, right?
yep,
So it doesn't mean that it doesn't have friction, right? Or
yep.
it does have friction.
It doesn't have friction because it's smooth.
Then why did you put F minus R1? Where did that friction force came?
F minus R1. Oh, when we are talking about forces, we are talking about the body as a whole, okay? So here in the X direction, I have R1 kat sini, kat situ, and I have F over here in my X direction. So that is why saya boleh tolak macam tu, F tolak R1, because I'm looking at the forces acting on the whole ladder. Faham tak?
No.
Why not? Sebab, because, are you confused about mu R?
I don't know where that friction force came.
Oh, down here, the friction is down here. At the axis of rotation tu kan ada friction.
So the friction force that acts in the down also acts at the upper end.
Also acts at the upper end. Okay, macam ni. Kejap, saya nak fikir contoh yang sesuai. How do I say this? Okay. Okay, so I have a box, right? So I'm applying force this way. This is the force that I'm applying. But my friction, so the motion is this way, right? The motion of the box is this way. That's the motion. It's not part of my free body diagram. And the friction, because it needs to oppose the motion, assuming that the floor has friction, the friction will be this way. Now, when I want to solve the forces for this particular box, what I do is I say, okay, so F is going this way. This is my Fy. This is my Fx. In the Fx, assuming that I don't have acceleration, so it's a 0, right? It's moving at a constant velocity, so there is no acceleration going on. So my Fx is equal to a 0. What I do is I say my F, I have Fx here, which is F cosine theta, which is going to the right, and I have friction over here, right? Here, I looked at the system as a whole. Even though the forces were acted at different places, I pushed the box on top, but the friction was acting down there. Okay, but I still could put it into my equation. Because why? We are looking at the system, the whole system, punya forces. Now, look back at the beam. The beam, I'm looking at the forces as a whole. So here in the X direction, I have R1 to the left, which is at the top here. I have friction to the right, which is acting down here. They are at different places, but they act on the same body. So I can include that into my force punya equation. Does that make sense? Friction kita kat bawah ni, down here. I hope you see my arrow here. It's down here. And we have R1 here. Okay, so the forces acting on this ladder is R1 to the left, friction to the right. So my equation is like that lah. In the case of the box, my friction was F cosine theta to the right and friction to the left. Even though one is on top, one is at the bottom, I could still write my equation like this. Betul tak? That's what we did because we assumed that it would act because it's on the same body. Sama juga macam ladder ni. Does that make sense? Faham tak?
Oh, okay, doctor. Thank you.
Okay. So when we are talking about forces, we look at the system as a whole. But when we are talking about torque, then we look at specific points because kita kena tengok perpendicular force to the beam and we have to know what is the length to the axis of rotation. So torque is the equivalent to force in the angular quantity, but it's not exactly the same. Okay. We still look at all the forces acting on the body to determine which way is the rotation. Yes, we will also need to know what is the length. So the length tu dah berbeza-beza. But in the case of forces, we just assume kita just masukkan force saja lah. We don't have to care about the length. Okay, even though it's at different position, we can just put it into our equation. Okay, I hope that's clear. Any other questions about this one?
Dr. Nat, let's say the surfaces now, let's say both are rough walls, R1 and R2, the contact forces happen between the ladder and rough walls. So can we assume R1 and R2 to have the same value?
Not sure, because sometimes your friction can be different because it's dependent on the surface. The friction on the floor and the friction on the wall selalunya lain kan? Sekejap, saya rasa lain kan? Kita punya floor selalunya lagi licin daripada dinding. So the friction is different there. But if you have both ends ada friction, then it won't move, right? So you don't have rotational motion. There's no torque. You will only have F net equals to 0. Okay, betul lah. You don't have rotation pun. Memang dua-dua lah tak ada rotation. But in that case, you don't have axis of rotation because both ends are not moving. So there's no axis of rotation, there's no torque to solve. Faham tak?
Faham. Thank you, doctor.
Okay. Any other questions before we move on? Is everyone okay? Okay, Dah tak nampak korang, pasal saya tengok rata-rata. Okay, so let's move on. So that was torque equals to RF, right? So now we are talking about work and power by torque. Yes, we have work and power by torque because torque is the equivalent to force in the angular world. So of course they want work and power as well. So in the linear world, we have work equals to F times displacement, right? Whereby displacement should be parallel to force, or force should be parallel to displacement. Okay, so this is your equation in the linear world. So F should be parallel to displacement, which is why you had the dot product. Because why? Dot product equals to a cosine. So this, it becomes fx cosine theta, or f cosine theta x. Sama je lah. But basically it wants to solve the F to be perpendicular to displacement. And we know that RF is equal to torque, right? So torque times d theta is equal to work done. Okay, jap Okay, sorry, I wasn't clear about this. Okay, again. Budak ni. Okay, again, work done by a force in linear motion is work times displacement. Sorry, force times displacement. Force times displacement, whereby force should be parallel to displacement, which is why you have the dot product. Okay, and we know that S equals to R theta. Okay, what is S? S is the arc length. What is arc? Arc is, this is the circumference. If I have theta, so this is my S. Ni equation untuk cari S sahaja. Kalau kita punya angle is 2 pi, right? If our angle is 2 pi, then our S is the whole circumference. So it becomes 2 pi r, right? Remember, so S equals to 2 pi r when the theta is 2 pi. Now I have a specific theta. So the equation for that is r theta. Okay, kalau kita masukkan equation ni pun, it makes sense. So R is r, and theta is 2 pi. So the length of the whole circle is 2 pi r. But if we are looking for a specific angle, so this just becomes theta. Okay, if your theta is 10, then just put 10. Okay, whatever that is. Okay, so that S equals to R theta. Just a little recap there. So S equals to R theta. So what I do here is I'm gonna say if this guy wants a ds, the change in S or the small change in S, I need to have my right equation to have d as well, the small change as well, right? Because I said you can't easily get rid of d or delta. You must include it in both sides of the equation. If you have it on the right, you must have it on the left. Sorry, terbalik. Right, left. And then R is d theta. Okay, so I'm going to put that into my equation. So now it becomes F. I'm substituting ds for R d theta. So RF is equal to tau. So that is how I get my tau d theta. Okay, so your work done when you have torque is torque times d theta. D theta is your change in angular displacement. So torque times the change in angular displacement gives you work done. Okay, so let's write that down. Work done is torque times the change in angular displacement. That's your first one. So that is work done. Work done is in joules. Okay, and then we have power. Previously, we learned that power is the is the rate of work done over time, right? It's joules per second. So sama juga, we're going to put this over dt, put this over dt, we will get power. So d theta over dt is simply omega. So P is tau omega. Omega is angular speed. Okay, so these are the two equations. The unit for power is joules per second or watt. Okay, sama juga walaupun angular quantity. The unit for work is also joules, even though we used torque to solve for it. Okay, so that is your equation. Work done is torque times d theta, change in theta. Okay, if this confuses you, just write d delta theta, sama. Okay. So those are two equations. Apart from torque is RF perpendicular. Okay, torque is a vector. Okay, what else? Okay, betul tu. Okay, and then we also have rotational kinetic energy. Told you, physics ni mengada-ngada, dia nak semua sama. Okay, so if we have kinetic energy in the linear world, the rotational should have it too. So K equals to 1/2 mv squared. This is linear kinetic energy, right? And I told you V is equal to R omega. We learned this before, so I'm going to substitute that into my V. So this gives me 1/2 mass times R omega squared. And then I have, thus for a rigid body, the kinetic energy is the total energy of all particles. Okay, remember I told you for a particular ball, we have many particles, and because we have to consider each one's length to the axis of rotation. I know torque is very annoying because we have to consider the length of each atom. And because we had to approximate the length of each atom, which is how we come up with the eye for different shapes, right? I told you this before, which is how we come up with eye of different shapes. So sama juga kat sini, the kinetic energy of all the particles over here is equal to the net 1/2 mr squared omega squared. And we've seen this one before. It looks like I, right? Which is the moment of inertia. So 1/2 I omega squared. Now, this one is the derivation for a generic body. For generic object lah, generic object. So let's say you have a cylinder. So cylinder dia ada the moment of inertia, which I don't remember what. Let me check. Here. Is it? So cylinder is 1/2 mr squared. Oh, okay. Let's use a different one. Don't use cylinder. Let's use a uniform sphere, which is a ball, right? Let's use Earth. The moment of inertia for Earth is 2/5 mr squared. So the I over here, you should use it depending on your shape. This derivation is just for generic situation. Sebab dia nak equatekan to angular quantity. So your K for angular quantity is 1/2 I omega squared. Your I should depend on the shape of your object. Because why? We already have this approximation for a bunch of atoms inside the object. Okay. Cuci nak bagi tahu. So K is 1/2 mv squared. K untuk rotational is 1/2 I omega squared. If you don't want to remember the rotational one, sama je, 1/2, the mass equivalent is I, the V equivalent is omega. So sama je. You don't have to memorize sebenarnya. Okay, so we also have work energy theorem for an object in linear motion. So this is chapter 4. Kita dah belajar ni. Chapter 4 kot, tak ingat. And then its corresponding definition for a rotating rigid body, we also have this in rotational, surprise, surprise. So work done, work total is 1/2 I omega final squared minus 1/2 I omega initial squared. Sama je, don't have to memorize. So this is the work energy theorem when you have an object of different speeds. Okay, so when should we use this equation? Good question. So let's use this. I think example 8.5 uses this. How much net work is required to accelerate it from rest? Okay, let's do example 8.4 first. Okay, so kita dah belajar torque equals to RF, perpendicular, power equals to, so torque, omega, wow, I'm surprised I could remember that. Plus 2 power, and then we have work equals to tau, torque d theta, or the change in angular displacement. So here an engine delivers a torque of 280 Newton meter at 3,800 RPM. So this is our omega, which is not in SI unit. So convert to SI unit. Oops. Okay. What is the power of the engine? So P is torque omega. So torque is 280 Newton meter. That's already in SI. My omega is not, so I have to convert that. 3,800 revolutions per minute times with 2 pi.
Doktor, torque dia 280.
Oh, sorry. Thank you. So what that is 1 revolution times with 1 minute, 60 seconds. So the answer should be, don't know, betul tak? In example 8.4. 397.94 radians per second. Okay, easy. You just use the equation. For you to do that, you must remember the equation. Okay, so example 8.5, a merry-go-round, assume it's a solid disk. Solid disk punya I is 1/2 mr squared. Has a mass of 1,640 kilograms and a radius of 7.5. How much network is required to accelerate it from rest? Tanya, what is accelerate from rest? So omega is 0 initial at the rate of 1 revolution in 8 seconds. So dia nak kita nak rotate at 1 revolution in 8 seconds, which means it's 2 pi, because 1 revolution is 2 pi radians over 8 seconds. So that gives me 0.79 radians per second. Okay, again, how much net work is required? So here it's asking you what is the work done untuk rotate it from rest to that 0.79 radians per second. So using the work energy theorem that we learned earlier, which is this equation. So we have this, which is from rest. We know this, we know what it wants, right? So let's put it into equation. How do I find space? Sekejap ni. So here my work energy theorem is work total is 1/2 I omega final squared minus 1/2 I omega initial squared equals to, this guy becomes a 0 because it starts from rest. So then nak tanya, what is the network required to accelerate it from rest to rotate at a rate of 1 revolution in 8 seconds? So 1/2 mr squared, 1/2, 1640, radius is 7.5. Okay. Okay. So omega final is 0.79 squared. So that is your work done. Okay.
Kenapa
So
dia kali half kat tu?
sebab I for solid disk is 1/2 mr squared. This 1/2 is this equation. This is the 1/2. This 1/2 is mr squared. Ni I. Betul tak? Ke saya salah equation?
Betul.
Betul lah? Check. Okay, it's 1/2 mr squared. Okay, so 1/2, the I is 1/2 1640 7.5 squared. Okay, ni I equals to mr 1/2 mr squared. Yang ni pula omega. Yang ni memang 1/2 lah. Okay, so it should be easy if you know the work energy theorem. Okay. So kalau dia tanya how much net work is done and they have a bunch of different speeds, you can use the work energy theorem yang linear. If they give you V in linear, if they give you speed in angular, you use the angular punya. Okay. Okay, but my question here is, dia cakap macam ni how much net work is required to accelerate it? Sekejap What happened? Okay, nothing, it's just drama. Tanya how much network is required to accelerate it from rest. So sometimes people get confused to say that 1 revolution in 8 seconds is the acceleration. Okay, I'm just putting it out there. Some people get confused when the question says what is required and we have 1 revolution over 8 seconds. So they say, okay, 2 pi over 8 ni is the acceleration, which is wrong because this guy is radians, this guy is second. Radians per second is omega. So if you are not sure, you look at what they give you, you put it into the equation and see what is the unit. Tengok unit Tengok unit, determine if it's acceleration or if it's angular speed. Okay, the question says required to accelerate. When we have 2 different speeds, we will get acceleration. When we have omega naught, we have omega final that is not equal to each other. It can speed up, it can slow down. When that happens, we can have acceleration. Okay, so jangan confuse kat situ. Okay, I know your weakness, at least for my students, is understanding the question. Okay, so take note. Tulis dulu, what is the unit? If the unit is radians per second, then it's giving you angular speed. If the question says 1 revolution in 8 seconds per second, then you have 2 seconds there, then it becomes acceleration. So please read the question carefully. All right. Okay, this comes the interesting part. Okay, I like this one. Okay, so angular momentum of a rotating particle is defined as L. So your momentum in linear is P, right? P equals to mv. And the change in P gives you impulse, which is force times time. Kalau tak ingat tak apa, saya bagi tahu ni. So momentum is P equals to mv. Dia lebih kurang dengan kinetic. kinetic, but it doesn't have 1/2, and the V is just sekali je lah, so P equals to mv. So that is your linear guy. For the angular world, we have, of course, we have the momentum as well. Kejap. Excuse me, baby, slow down. Okay. Mana tadi? Okay, so V ni kita masukkan dia punya, oh my god, I'm distracted. Kejap. Okay, sabar. I told you it's going to be interesting. Saya nak cerita dia punya equation dulu. Okay, so V equals to R omega, right? So I'm going to substitute that. L equals to mv R omega. Apa ni? Kejap. Silap. L equals to R mv. Okay, so here it's V equals to R omega. And then therefore angular momentum is L R mv. Kejap, saya confused. So R times P, so this becomes R mv. So R mv, V is R omega. This becomes mr squared omega. So mr squared omega, mr squared, you've seen this before. It looks like moment of inertia. So L is, am I unmuted? Have I unmuted myself? Oh yes, wait. Okay, so L becomes I omega. Okay, so that's your equation for momentum. If you don't want to memorize the equation, P equals to mv, L equals to, the equivalent for mass is I, the equivalent for V is omega, so you don't have to memorize sebenarnya, provided that you memorize the equation for momentum. Okay, so that is, L is I omega, L is the momentum punya term untuk, L is the momentum punya term in angular quantity. Okay, so from Newton's second law, torque is equal to I alpha. We already learned this, I think. Dah, yes. So torque equals to I alpha, but angular acceleration is alpha d omega over dt, right? So dia substitute lah alpha ni into, the alpha goes into here. So dia letak I d omega dt, so they're not rearranging this. So what happens is, kenapa macam blur ni? Sekejap. Tadi kita belajar Li omega. Okay, so dia nak samakan benda Allah ni dengan torque. Okay, so that is what it's trying to do. Okay, so torque equals to I d omega dt. So yang ni kan ada, yang ni kan ada I omega. Yang ni ada I d omega dt. So what I can do is I can say, okay, so if I want to make this sama, I can put dt over here, I can put dt over here. So now torque equals to I d omega dt or L dt, right? So dl dt is actually torque. Okay, so torque is equal to the change in momentum. Okay, have you seen this one before? Does it look familiar? Yes, it should be. Okay, because you had the change in momentum for linear, which was change in P equals to Ft. Tak adalah sebiji sama kan? Tapi here you have torque equals, the change in L equals to torque. Okay, so remember torque ni lebih kurang macam F, lebih kurang je lah. So the equation is slightly different in the sense that the change in momentum ada T lah. Okay, so but I'm just trying to make this simpler for you guys to remember. So the change in momentum is equal to torque. So if torque is equal to 0, it means that L final minus L initial equals to 0, right? Which means that L final is equal to L initial, which means that L is a constant. So L is constant. So here, when torque is 0, you have conservation of momentum. So this is called the conservation of angular momentum when torque is equal to 0. Okay, tu je yang kena ingat. Conservation of angular momentum when torque equals to 0. What is the equation for L? L is I omega. Okay, so if net torque equals to 0, then L is constant, or you have the conservation of angular momentum. Now, the principle of conservation of angular momentum is interesting because, okay, this is where I like the most. Let me show you, sorry, YouTube. Figure skating, angular momentum. Okay, can you guys see this? Oh, saya belum share lagi kan? Yep. Share screen. This one. Boy. Kejap, can you guys hear the video as well? No? Dengar tak?
Tak dengar doktor.
Oh, tak dengar. Okay, sekejap ya. Nampak tapi tak dengar kan?
Pause.
Share computer sound. Share. Sekarang dengar tak?
Dengar.
Okay.
Okay.
Through years of tireless training, skaters must learn to understand moment of inertia or momentum. Must learn to understand and use angular momentum to become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
Okay, so it's saying that if you want to become a champion in figure skating, you should know the principle of conservation of angular momentum. Cool. Maksudnya saya boleh menang lah. Okay, share screen. Ni chapter 9, sorry. Banyak pula. Budak dah sampai balik dah. Stop share dulu. Chapter 8. This is not the slide. You can guys see this chapter 8 punya screen?
Yes.
Okay. Okay, so let's talk about what happened just now. Bising lah budak ni, sekejap Ish, annoying. Okay. 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 So if you were to refer to your module, we can see that when our page 98. Kejap saya lukis lah. Mana nak bezakan dua ni? Okay. So I can. So the equation for I for a solid cylinder is the I is 1/2 mr squared, right? Okay, let's just use this example dulu. So now the figure skater, so using the principle of conservation of momentum where L should be a constant, right? The figure skater is not a, there's no net external torque applied to the figure skater. She's rotating on her own lah. So what that means is, when she extends her arms, what she does is, alamak, kenapa macam buruk sangat ni? So what she does is she is increasing her radius, right? Imagine the figure skater like a solid cylinder. When she extends her arms, she is extending the radius. So let's say when she extends her arm, the radius is 10. And when she is not extending her arms, right, her radius is just 5. Buat satulah senang. 1 meter. Panjang gila mat tangan kan? Okay, 10 meter. Okay, so now when she is extending her arm, her I is 1/2, assuming her mass is 50. Okay, so R is 10 squared. So this is I1. And then this is I2, 1/2. When she is not extending her arms, she is putting her arms on her side. Her I becomes smaller.
What's painting?
This is bigger.
What this one? What this one?
No.
Angry.
Yeah, mommy's angry. Okay, nah. Main benda lain. Okay, so I is bigger when she extends her arm. I is smaller when she's not extending her arm. Okay, so remember, L is a product of I and omega. Okay, so here your I changes. So if this guy is a constant, if I is bigger, your omega must be smaller. And if I is smaller, your omega must be bigger. So when she is extending her arms, she is going to go, she ni extend sebab dia increase in a moment of inertia, extend, slow down. When she is not extend, they speed up. Okay, so let's take a look at the video again. Was that really the case? When she extends, she is supposed to go slow. When she is not extending her arms, she is supposed to go fast. Okay, so let's see. So share screen. Where is it? It's here. Share. Okay, let's see.
As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia. She increases her moment of inertia.
Mana?
No net external torque acting on her. Angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
Yay. Okay, so that is it. So betul when we increase our inertia, we are reducing our speed because we have to conserve our angular momentum. Okay, is that clear for everyone?
Yes.
Okay, so let's share my presentation.
Says that the angular momentum of a system remains constant unless the system is acted upon by net external torque. Now,
Shush. Okay, chapter 8. Okay, so let's do this example. A person stands, hands at his side. So he assume a cylinder. This is the guy on a platform that is rotating at a rate. So he's on a platform. This platform is rotating at 1.3 RPS. What does RPS mean? Revolution per second. If he raises his arms to a horizontal position, so he's increasing his moment of inertia. Wow, that's ugly. If he raises his arms to a horizontal position, he's increasing his I. The speed of rotation decreases. So now it's 0.8 RPS. Why? By what factor has his moment of inertia changed? Okay, why? Because, does anyone want to answer that? Why? Why does it change? Why does the speed decrease?
Because as the radius increases, moment of inertia increases as well. And since momentum is constant, so when I increases, then angular velocity decreases.
Yes, betul. So if the question asks you why, you should answer completely like that lah. You mention about the equation, and then what happens when you change the I. Okay, cerita macam Bell tadi. Okay, by what factor has his moment of inertia changed? Dia tanya, bila dia extend his arm, by what factor has his moment of inertia changed? So if this is I2, this is I1, tanya what is I2 in terms of I1? Okay, why? Because it's asking how does I2 change in relation to I1? So what is I2 in terms of I1 lah, basically. So to do that, we have to write our equations. So let's erase this. Should I erase it or not? I should, because it's taking too much space. Okay, I'm gonna put this somewhere else. Okay, extend is I2, I1 is when it's not extending. So put it, I1 is here, I2 is here. It's I2. Okay, buang ni. Alright. So by logic, kita dah tengok video tadi, by logic when we extend, our speed should decrease. This guy, the speed should be speeding up. Okay, so let's write the equation. By logic kita dah tahu dah, but the equation should be there as well. So here our omega 1 is 1.3, sorry, 1.3 revolutions per second. I want to change that to SI, so that becomes 1.3 times 2 pi per revolution second. So revolution dah potong, revolution here, potong. So 1.3 times 2 pi is just 2.6 pi radians per second. Okay, boleh you can put it in value form. You can just write it as pi itself, boleh juga. Then you have omega 2, which is 0.8 revolution per second. 0.8 times 2 pi. So that would give you apa? 1.6 pi radians per second. Okay, kalau saya disilap bagi tahu And then we know that our L1 is equal to L2 because we are applying the principle of conservation of angular momentum. So L1 is equal to L2, or L is constant. Can write that L is constant. Therefore, the equation for L is I omega, right? So I1 omega 1 is equal to I2 omega 2. And what is I1? I1 is, I don't know, I'm looking for it. I1 and omega 1 is 2.6 pi. And I2 is, I don't know, I'm searching for it. Omega 2 is 1.6 pi. So the question is asking you, what is I2 in terms of I1? So I2 in terms of I1 is I1 2.6 pi over 1.6 pi. So this can cancel out. So 2.6 divided by 1.6 is 1.63 or 1.625. So this is I1 times with 1.625. This is I2. Okay, so here the I2 is when we are extending. So I2 is 1.625 greater than I1, which makes sense because I1 is when our moment of inertia is small. So I2, the moment of inertia is 1.625 greater than I1. So it makes sense. So your answer is right. Okay, I know you're tired, but please bear with me. Kita nak laju-laju habiskan, then kita will take our 1 hour break, okay? So the dynamics rotational motion. Yep.
Sorry, Doctor, can you show the slide just for like 3 seconds?
This one?
Thank you, Doctor.
Okay. So this is your final answer.
Thank you, Doctor.
All right. Any questions about this one?
Doctor,
Mm.
how do we know that our L is constant?
Because in the question, they didn't say there is a net torque applied. Unless they tell you there is a net torque, then you will assume that angular momentum is conserved.
That means that we always assume that the angular momentum is conserved, that is torque is equal to 0 and L is equal to 0 unless you say that is another net torque is applied.
Your net torque is equal to 0 and your L is a constant or a 0 unless a torque is applied. Yes, betul. How do you know if torque is 0 or not? Torque is equal to RF. Kalau tak ada force applied or there is no acceleration because F equals to ma, there's no force applied, there's no acceleration going on, then yes, no torque. Okay.
So no torque means that no angular momentum. No, the angular momentum is conserved.
Yes, when there is no net torque, angular momentum is conserved. Okay, basically, no F, no torque. Huh?
Alright, thank you, Doctor.
Doctor, how do you know W siapa bagi W siapa? I mean, omega apa bagi omega apa?
Here, dia tanya by what factor has his moment of inertia changed? So, dia tanya bila dia extend tangan dia, kan? If he raises his arms, blah, blah, blah. So, dia tanya by what factor has his moment of inertia changed? Bila dia extend tangan dia, by what factor has his moment of inertia changed? Maksudnya I2 in comparison to I1 lah. Does that answer the question?
Oh, okay.
So this
Thank you,
question
Doctor.
is asking I2 in comparison with I1. Okay, kalau tak pun tanya tau. Kalau tak, if it doesn't make sense. Alright, next one. So this is the table. Mesti dah bosan dah dengar saya cakap benda ni ulang-ulang, but I'm going to repeat myself again. Anyways. So displacement is x, angular displacement is theta, velocity is v, angular velocity is omega, acceleration is a, angular acceleration is alpha, theta, these are all Greek letters except for I, L. So torque pun Greek letter juga. Mass, the equivalent is moment of inertia, momentum is P, angular momentum is L, force is F, torque is tau. Tau, itu macam ni. And then the relation is X R theta, V R omega, A R alpha. So semua ada R. Ini semua angular. Okay, ni semua linear. Okay, yang ni je yang boleh apply macam tu. So I equals to mr squared. Depends on the shape as well, but this is the general equation. And then you have angular momentum equals to Rp or I omega. But this is the relation to the linear. Terbalik kejap. Kenapa lah nak save sekarang? Terbalik tadi kita tengok linear, yang ni angular. Yang ni angular, yang ni linear. So momentum je yang terbalik. And then we have torque equals to R alpha. Okay, torque pun sama lah terbalik juga. So torque is R. Okay, this is linear and this is angular. Okay. Bising lah budak gemuk tu. Hish. Okay, and then the kinetic energy is 1 over 2 mv squared equals to 1 over 2 I omega squared. Work is force times displacement. Can you turn that down?
No, I can't.
Yeah, it's a dinosaur robot. Okay, go sit down over there.
Roar!
Okay, bye-bye. And then work is torque times this change in theta. This change in theta. And then power is F times V, or the just work done over time. Okay, this is FG over second. This is V juga, so FV. Sama je. If you can't remember this one, remember what works for you. So power is work done over time. And then you have power torque times alpha. Apa nama dia? Omega. Torque times omega. And then you have Newton's second law, work energy theorem, conservation of momentum. Hey Yusuf, turn that down. Lower down. Lepas tu F equals to MA. Net torque is I alpha. Work energy theorem sama juga 1 over 2 I omega squared minus 1 over 2 I omega initial squared. And then you have conservation of momentum. When net external force is 0, total momentum is constant. Remember this equation, Ft. When F is 0, P is constant. Sama juga kat sini. When torque is 0, your L is constant. Your L is constant. Right? So that is a good. Yep.
Can I see the previous slide
Okay.
for 3 seconds?
3 seconds. 1, 2, 3. Dah. Just kidding.
Slide 59.
Oh, lagi satu. This one.
Ya dah.
Alright. Okay, so we have one more. Yep.
Dr. Nat, before we enter rolling bodies, I have a question.
Yep.
It's based on a question web design. So there's a plank, a horizontal plank, and then there's this guy standing on the plank. And there are 3, to make it simple, let's have 2 strings. So like 1 string on the left and 1 string on the right. And each string has a tension that makes this entire plank string system in equilibrium. So we have this guy standing on the plank, right? Think, doctor. So we know his weight is acting downwards. And then he will have an R if this is a free body diagram.
He will have an R. With respect to the axis of rotation, right?
Correct, doctor.
Okay, lepas tu?
Right, then doctor, since he will have a reaction force because of his contact with the plank, then when we consider the torque, wouldn't the torque caused by the reaction force cancel the torque caused by his weight?
Okay, we already talked about this when we first entered this chapter. I told you the reaction force is acting on this. Oh, ya Allah. The reaction is acting on this guy, not on the beam. Oopsie. So this is R, this is mg, right? So the only thing that affects the beam when the guy is standing on it is the load. So the guy becomes the load on the beam, whereas the reaction is from the free body diagram of this guy. So we don't care about his reaction. We don't care if he dies or whatever. We just want the load on the beam because we are looking at the load on the beam to find out what is the torque on the beam. As for this guy, he can have whatever mg, he can have tension, he can have reaction, but he is not part of the system. He just
Doctor,
acts
that
as a
means
load.
we only, sorry doctor, that means we only take R, that R experienced by the guy into consideration when we use F net equals 0. Okay, doctor?
For if you are drawing the free body diagram for this guy, yes.
Thank you, doctor. It makes sense.
Okay. Betul ke? Faham ke? Did everyone get that? So you only consider the guy as a load. The reaction force is acting on that guy, not on the beam. Whereas if I don't know what the axis of rotation is because I haven't looked at the question. Let's say that it's here, so your R should be, I don't know. I haven't seen the question sebenarnya, so I can't say. Okay, so remember the reaction untuk the beam is only at the axis of rotation, or if it's in contact with the wall, the guy on the beam only acts as a load. Okay, and the reaction force is for the guy. The reaction force is for the guy, not on the beam. Okay, okay, I hope that's clear.
Got it. Thank you, doctor.
All right. Okay, so now kita masuk rolling bodies. Rolling bodies can be considered as a combination of linear motion and rotational motion. Please imagine your car tires. They are rotating and also moving forward. So that is translational, it's moving forward, it's translational motion. Moving forward, moving to the right, to the left or whatever. It's also rotating, right? If it is just rotating, and not moving forward, then you just call it rotational motion. Okay, but if it's rotating and also moving forward, then you say that it has rotational and translational. Sorry, I'm distracted by this dude. Okay, lepas tu, imagine a bicycle tire. Yusuf, can you turn that down, please? Yusuf. Okay. So I'm back. So here, I'm drawing the free body diagram for this bicycle. If it's not on an incline, this is a straight path, macam jalan biasa je. So the mg is going down, I have friction. If I am rotating this way, motion is to the right, right? So friction opposes the motion, so friction is this way. Whereas if I'm on an incline and I am rotating clockwise, the motion is here, my mg is down here, that's my mg, and then I have friction. And the radius for the bicycle tire is here, which means that if I were to talk about torque, I can say friction, the friction is perpendicular to the moment of arm. Okay, so R is remember R is the distance of the force. Let me write that properly. Okay, R is the distance. If you guys can remember, R is the distance between the force. Saya dah unmute ke? Okay dah. Between the force and the axis of rotation. So here, the distance between the force and the axis of rotation is given by R. So your torque just became a little bit more complicated, but it's okay. We will learn how to do this. Okay. So if that's a free body diagram for that, do we have other examples? So here the total kinetic energy is linear plus rotational. The linear is given by the translational velocity, or the linear velocity, sorry, I shouldn't use translational. It's linear velocity. And this guy is given by the angular. So the tire is both rotating and also moving forward. So the kinetic energy is both the linear velocity and also the angular velocity. So you have two terms to calculate for your kinetic energy. So if they ask you what's the total kinetic energy of a rolling body that's rolling on an incline, so you have to use these two terms, the linear and the rotational. When do you not use this equation? For example, this is your incline, this is your box. You push the box, it goes down. This is the motion. In this case, the kinetic energy of the box is just 1/2 mv squared. Is your box rotating? It is not, because how can a box rotate, right? It's not circle. So if that's the case, you use this equation. However, if you have a tire, it's rotating, also it's rotating as well as moving forward, then you use this equation where it has both linear and angular quantities. Okay, so we have to apply the conservation of energy for rolling bodies. So if I start at rest, okay, and I start at a height, so the energy at point 1, right? The energy at point 1, I can write my equation like this: mgh plus ke. Based on the conservation of energy, the energy at E1 should be equal to E2. E2 should also be mgh plus ke. Kita assume tak ada friction sekarang ni. This guy, no friction. No friction. So the energy is conserved without non-conservative forces acting on the object or the system. So at E1, I am starting at rest, which means that my ke is equal to 0. So my E1 is just mgh. At E2, my h is a 0. Let's say my h at this point is 10. At this point, my h is a 0, which means that my mgh is 0. So now, all my mgh has been converted to ke. If E1 is equal to E2, mgh is equal to ke. So ke, in this sense, we have rotational and also translational. We have rotational and translational. So this becomes 1/2 mv squared, 1/2 I omega squared. And this becomes mg times 10, whatever that is. Okay. So that is how you use the conservation of energy to solve for rolling bodies down an incline. Okay. Okay. Okay, so let's do this example and then I'm going to give you guys a break before we go into this one. So let's do this example and then we will have our break. So bowling ball of mass 7.3 kilogram and radius 9 centimeter. Convert this to SI unit. Rolls without slipping down a lane at 3.3. So this is the V, 3.3 meter per second. This is the mass, 7.3 kilogram. This is the R. What does slipping without slipping down mean? Okay, so if I have a lane, if I am slipping, if I am slipping maksudnya saya tengah tergelincir. If I have a ball, saya tengah tergelincir, I'm not rotating, I'm just moving forward. This is my object slipping. What is slipping? Slipping is tergelincir. If there is another word for this, I don't know, but my best guess for it is tergelincir lah. Kejap, tulisan ni sangat buruk. Tergelincir. Okay, if I am rolling without slipping, which means that my ball is rotating as well as moving forward. So here I have both the 1/2 I omega squared. I also have 1/2 mv squared. If I am slipping, I only have 1/2 mv squared. Because why? Bila saya tergelincir, saya tak rotate. If you guys can imagine, kalau bola tu tengah tergelincir, dia tak berputar. Dia hanya bergerak ke depan. Sama juga macam kereta, when the tire loses grip from the road, dia dah tak ada friction kan? It just gelincir. It does not rotate. That's why we lose control of the car. Bila hujan, there's no friction, tergelincir. The tire is no longer rotating, but it's slipping. So it's slipping, which means that you only have 1/2 mv squared. When it is rolling without slipping and it's also moving forward, you have both terms. You have angular, you are rotating, you are also moving forward. 1/2 mv squared. So now it says without slipping down a lane. So we have both terms lah. So that is 1/2 mv squared plus 1/2 I omega squared. Sabar, I know everyone's tired. I am also losing my voice here, so please bear with me. So V is 3.3 squared plus 1/2. What is the I for a bowling ball? I believe it's 2/5 mr squared. Correct me if I'm wrong. Okay, so that's 2/5. M is 7.3. R is 0.09 squared. Sorry about that. Okay, and this whole thing is squared. No, that's baru I. Omega is, you know, V is 3.3. Omega is V over R. So 3.3 over 0.09. So this guy times with 3.3 over 0.09 squared. Okay, so let me write that down cantik-cantik sikit. So that is 1/2, 7.3, 3.3 squared. I hope I have enough space. 1/2, 2/5, 7.3, 0.09 squared. So that's your I. Then your V is 3.3, 0.09 squared. So this is your total kinetic energy, whatever that is. Punch in your calculator. Okay. Oopsie. Can someone calculate this for me, Jap? While I clean this up for the next question. Oh, how do I do this?
23.85.
23.85. May on I do.
Akil.
Okay, thank you, Akil. 22.85. Sekejap.
Juga.
Sekejap. Kenapa dia tak select? Oh, okay, thank God. Dude, cooperate. Okay, tak apalah. Nanti itu saya tulis. Okay. So that is your answer. The answer is 22.85 joules. Okay. Okay, so the next question before we take our break. A ball of mass 0.5 kilogram and radius 3 cm rolls without slipping. Maksudnya dia tak tergelincir lah. Maksudnya kita ada rotational and also translational, moving forward. Down an inclined plane that is 30 degrees above the horizontal. So the ball is 0.5 and it has a radius of 0.03 meter. If the length of the plane is 0.8 and the ball starts from rest, what is its speed? So omega is 0, omega dot is 0. What is its speed when it reaches the end of the plane? Okay, I think I need to do this on Word because it's taking too much space now.
Sorry, Doktor.
Yep.
Yang tadi tu 55.6.
Okay, 55.6. Got it.
Saya silap tolak.
Alright. Tolak 55.6.
Tak nampak tadi.
Tolak kat mana? Ada tolak-tolak ke?
Saya tak nampak simbol tadi.
Oh, okay. Okay, let me do this on Word. Okay, kejap Word. New document. Okay, sikit lagi. Bear with me. So, share dulu. Sharing balik. Where is it? Okay, this one. Okay. Draw. Okay, let's do this quickly so that we can have our break. Kenapa dia tak nak ni? Please cooperate. Tak nak draw pula dah. Okay. Hello. Okay, thank God. Oops. Okay lah, anggaplah incline tu cantik. Okay, so I have a ball that starts from here. The length is 0.8. So this guy is 0.8 meter, which means that we can calculate for the h over here. So how do I do that? Opposite over hypotenuse. So that is a sine theta. H is, if this is h, this is 0.8 meter. So sine 30 is h over 0.8, which gives h as, tak tahu. Lepas tu, the balls.
0.4.
Okay, 0.4. Thank you. The length of the plane is 0.8 and the ball starts from rest. So omega naught is 0. V naught is also equal to 0. What is its speed when it reaches the end of the plane? Okay, so we are using the conservation of energy here. And I told you E1 and E2 should be equal. The energy at the initial point and the energy at the final point should be equal. So E1 equals to E2. What is the equation for E1? E1 is, it should be consisting of mgh, and we also have Ke here, and E2 should also have mgh plus Ke. Here, Ke is 0 because we are starting from rest. So the E1 is just mgh, m is 0.5, g is 9.81, h is 0.4. Okay, whatever that is. And at the end point, the energy should be the same, but here the h is 0. So this guy becomes a 0. So now it becomes 1 over 2 mv squared plus 1 over 2 I omega squared. Okay. So now it's asking you to find the v. What is the speed when it reaches the end of the plane? But we have two different v's, v and omega. So now my question is, how do we solve for these? How do we solve for the speed? Oops. Anyone? How do we solve for the speed? What should we do here? We have this equation. How should we solve it?
Tukar angular velocity kepada velocity.
Tukar angular velocity to velocity. Yes, correct. So we know that v equals to r omega. So we can substitute that into our equation so that we only have one unknown, which is our v. V squared plus 1 over 2. It's a bowling ball, right? It's a ball. So 2 over 5 mr squared. R squared. Omega is v over r. So I'm going to put that here. V over r squared equals to 0.5, 9.81.
1.92.
Okay, thank you. 1.92. Okay, 1.92. So this is a V. Okay, so I have two R squares here. I have R squared dekat I. I also have R squared here. Which leaves me with 1/2 m V squared plus 1/2, 205 mass V squared 1.92. So now I can solve for V because I know what my mass is. It is 0.5. Okay, so the answer is, oh, I didn't do it. Oh, yeah, I did it. 2.36. So V is 2.36 meter per second. Okay, so they are asking you the speed. What is the speed when it reaches the end of the plane, which is, what is the kinetic energy? Nak solve it, kita cari kinetic energy at the end of the plane. What we did was conservation of energy. Okay, we can take our break now. Please come back at 11. I'm gonna stop sharing now. I'm gonna stop recording as well. Nanti kita start a new session lah. Basically, I will give you a new link. All right. So I'll see you in 1 hour. Have your breakfast. Have some rest, whatever it is. Come back refreshed.
Okay. Thank you, Doctor.
You're welcome.
Thank
Yes,
you,
Belle.
Doctor.
You're welcome. Okay, bye. If you want to leave, you can. Yep, Belle.
Sorry, Doctor, can you show slide number 42 before you
Slide
sharing?
number 42. Kejap. Silap. 42. Share screen. Kenapa dia share ni? Sekejap. Okay, 42. This one. Okay, Belle? Any questions about this one? Okay, Belle dah hilang. Or was it not Belle?
Okay, thank you, Doctor.
Okay, you're welcome. Bye. Okay, bye guys. I'll see you in 1 hour. We'll give you the link later.
Thank you, Doctor.
Okay, bye.
Doktor,
Oh, yeah.
tadi E1 dengan E2 tu kita equate kan?
Yes, we did. That I'll show you again.
Memang ada V yang tak ada value Yang
Memang.
unknown
Memang ada V yang ada. Kejap. Not sure what that means.
Satu given
Satu given, no. V dua-dua tak given. Oh, sorry. V initial given. Omega naught as 0. Tu je lah yang kita tahu.
Oh, alright. Thank you, Doctor.
Okay. So I'm going to leave this here. If you guys are ready to leave, just leave.
Memang leave bukannya biar terbuka macam ni tapi...
Tak. Just leave. I'll give you a new link.
Alright, thank you, Doctor.
Alright. Bye.
Thank you, Doctor.
You're welcome.
Thank you,
Bye.
Doctor.
In 1 hour. See you.
Thank you, Doctor.